Warning, this video contains spoilers. Here's what Interstellar could have looked like. Welcome back to Science Click. Today, let's try to remake the calculations from Interstellar. Released in 2014, Interstellar, directed by Christopher Nolan, left its mark on audiences by presenting realistic images of a black hole. But is the movie accurate? What is the speed of the ship? What are its dimensions? How does time behave around a black hole? What does the inside of a wormhole look like? In this video, we will go back over the journey of the film's characters and attempt to mathematically verify the accuracy of the different concepts. We will also try to rebuild some visuals from the movie. This may be a bit technical, but just keep in mind you don't need to understand all the calculations. We will at times rely on information from the book The Science of Interstellar, written by Kip Thorne, the main scientist behind the movie. This video was originally made in collaboration with the French channel Octave, which talks about science in popular movies. He usually doesn't make videos in English, but kindly agreed to let us translate his voice for this one. So don't be surprised if the visual style of the video changes at times when we present the storyline. At the start of Interstellar, the situation on Earth is critical. Humans are facing food shortages, air is close to unbreathable, dust is omnipresent. The planet no longer seems habitable. On this apocalyptic Earth, we follow Cooper, a former NASA pilot who lives with his two children. In the bedroom of his daughter Murphy, strange events occur. Events that Cooper ends up identifying as gravitational anomalies. One day, one of these anomalies mysteriously reveals coordinates, which once followed lead to a secret NASA base, as if the library had wanted to guide them there. In this NASA center, we learn that a wormhole has opened near Saturn, forming a passage to other planets, and that NASA is about to launch a critical mission. A space crew will cross the wormhole and try to reach 3 potentially habitable exoplanets. Of course, Cooper arrives just in time for the adventure. As a former NASA pilot, he is recruited and thus embarks on an interstellar journey aboard the Endurance. After takeoff, the crew goes into hibernation. The ship will take 2 years to arrive at the wormhole near Saturn. Is this travel time realistic? We can roughly estimate the speed of the ship by taking the shortest straight line between Earth and Saturn and factoring in the radius of their orbits. We can assume that the ship travels approximately 1.3 billion kilometers. Divided by 2 years, this gives us a speed of around 70,000 kilometers per hour. As a basis for comparison, the fastest ever manned flight was Apollo 10 with a speed of 40,000 kilometers per hour. Assuming that Interstellar's technologies are better than ours, this 2-year duration is therefore realistic. The characters need artificial gravity to feel comfortable. The Endurance forms a wheel which turns on itself and pushes the characters against its outer walls by centrifugal effect. The centrifugal acceleration is given by 4 pi squared r over t squared, where r is the radius of the wheel and t its period of rotation. In this scene, we can time a half period of 5.7 seconds, which gives us a total period of 11.4 seconds. This must equal 9.8 meters per second squared, the value of gravity on Earth. We deduce that the radius of the wheel must be roughly 30 meters or 60 meters in diameter. A fairly realistic value given the International Space Station is 70 meters across. The Endurance's crew wakes up near Saturn. We observe for the first time the wormhole that they will have to cross. A wormhole is a distortion of space, a sort of tube which connects 2 slices of the universe. It is difficult to draw because the surface of the tube is actually 3-dimensional, a volume within which the ship can move. light can also pass through it and we can receive an image of what is on the other side. But is its appearance in the movie realistic? To find out, let's try to simulate it. We start with a cylinder connecting two sheets of space. Let's smooth out this cylinder to have a better transition. For the movie, Nolan chose a very short cylinder and a relatively quick transition to get the appearance he liked. Let's place a camera and choose two images to represent the sky, the celestial sphere of each of these two universe slices. The camera receives light rays, some of which arrive directly from the same slice it is on, and others after crossing the wormhole. All these light rays arrive on the pixels of the camera. Without going into details, we can perform a method called ray tracing, which involves sending a light ray through each pixel of the camera and rewinding its trajectory to determine where it came from in the sky and what color is received by the camera on that pixel. In practice, this amounts to using the geodesic equation, a general relativity equation which allows us to trace trajectories through curved spacetime. By repeating the operation for each pixel, we obtain an image. A result which, when put in motion, is quite similar to that of the movie. We can now play around with varying the geometry of the wormhole to see what it might have looked like if Nolan had made different choices. With a very long wormhole, light can orbit several times before reaching us, and we can observe an infinite number of repeating images of the universe. In Interstellar, the Endurance enters the wormhole to cross it. We discover the inside of the wormhole. Is this scene realistic? To find out, let's move our virtual camera along the surface of the tube. This time around, the images are quite different from what the movie shows us. The visual effects team probably wanted to help the viewer better understand that the spaceship is moving along the surface of a cylinder and crossing into a fourth dimension. If this scene had been simulated, we could have witnessed hypnotizing images, such as these. Exiting the wormhole, the explorers arrive near a supermassive black hole called Gargantua. This black hole has planets orbiting around it, and our crew's first destination is one of them, Miller's planet. This planet is very special. It is completely covered in water, and its orbit is very close to Gargantua. So close, in fact, that extreme phenomena arise. Near a black hole, tidal forces are gigantic, and Gargantua attracts the planet more on one side than the other, distorting it and forming immense 1 kilometer high waves on its surface. Because of its proximity to the black hole, time also passes more slowly, so much so that for each hour that passes on this planet, 7 years pass on Earth. In short, Miller's planet is mysterious and deserves our attention. Let's start with the waves. Kip Thorne indicates that they stretch over 1 kilometer in height. How close to the black hole would the planet need to be for such waves to form? We can attempt a rough estimate. We can assume that these waves are in fact tides, generated not by the attraction of the moon, but by that of the black hole. The waves in the movie look thinner than simple tides. They might be closer to what we call tidal bores, but for a rough estimate, our approach should still work. The waves thus result from the combination of gravity from the black hole and the centrifugal effect produced by the orbit of the planet. We can calculate the resulting net force with Newtonian physics. This is the tidal force. This force displaces water from low tide, left and right, to high tide, up and down. The force supplies each water droplet a certain energy, which we can calculate as the product of the vertical displacement, which is the radius of the planet, and the average value of the force along this path. It is this energy brought by the tidal force which allows the water to rise. It must therefore equal the gravitational energy that the water acquires. From this equality, we can deduce the distance at which the planet should orbit for such tides to form. If the planet's dimensions are similar to those of Earth, knowing that the black hole weighs 100 million solar masses, then the planet should orbit at a distance of 4.5 billion kilometers. To compare, the Schwarzschild radius of the black hole, which we can deduce from its mass, is 300 million kilometers across. If we bring this diagram to scale and compare it to this image from the movie showing Gargantua as seen from Miller's planet, the result seems coherent. But is this close enough to also explain the strong time dilation? Each hour that passes on the planet corresponds to 7 years on Earth. Time passes 7 times 365 times 24 times slower, a factor of 60,000. For a static black hole, this is the time dilation, experienced by a planet in circular orbit. If we insert the distance obtained with the calculation of the tides, we get a time dilation of only 5%, far from what the movie shows us. There is an incoherence. To obtain a factor of 60,000, the planet would have to orbit just above the photon sphere, where light itself can remain in orbit. An absurd result, because any orbit so close is inevitably unstable. But this calculation is only valid for a static black hole. General relativity allows black holes to rotate. The faster a black hole spins, the more likely stable orbits exist near its horizon. The calculations are more complex, but we can determine that it is possible to reach a factor of 60,000, provided that the planet orbits 6,000 kilometers from the horizon and that the black hole spins at a trillionth of a percent slower than the speed of light. Extremely fast, but not impossible in theory. Of course, this situation remains incompatible with what the movie shows us. The visual appearance of the black hole is surely what brought attention to Interstellar. In France, Jean-Pierre Luminet had done a first simulation in 1979, but in 2014 it is the first time that we see such images in theaters. Could we reproduce these simulations at our scale? Let's try the ray tracing method. We place a camera in the center of a celestial sphere in front of a black hole rotating almost at maximum speed. General relativity allows us to rewind the trajectory of light rays to find their origin in the sky. Some rays are blocked by the black hole, and the corresponding pixels do not receive any light. In this way, we construct an image. The rays are deflected by gravitational lensing, causing optical distortions. We observe the shadow of the black hole, the area from which we receive no light. For a static black hole, this shadow would be a disk, but for a spinning black hole, it seems squashed on one side because space-time spins and drags light with it. In the movie, this phenomenon was reduced to render the visual effect less strange. Around Gargantua orbits an extremely luminous plasma disk. Let's place a disk in our simulation. We see that its image is distorted. The back of the disk seems folded above and below because the black hole bends the rays coming from it. In reality, such an accretion disk would be extremely hot. It would emit intense radiation which would instantly destroy the ship. The disk temperature has therefore been drastically brought down for the movie, implying that it is also very thin given its lower internal pressure. This plasma rotates very quickly around the black hole, such that the light we receive from it is propelled on one side and slowed down on the other. This is the Doppler effect. The disk appears bright and slightly blue where it moves towards us, and dark and red where it moves away from us. This effect was considered too strange and was not included in the film. We can play around with comparing our simulation to images from Interstellar. If they had included the asymmetry, the Doppler effect, and a higher temperature disk. While our interstellar mission is going on, back on Earth, the professor refines his mathematical model, trying to account for the discovery of the gravitational anomalies. This quest had already led him towards a very complex equation to solve, and his goal in solving this equation is to have answers about the nature of gravity and then use this new knowledge to launch a gigantic spaceship into space and save humanity. But we are not there yet. At this stage of the research, the professor's conclusion is that the gravitational anomalies must be caused by something outside our universe. According to him, our space could be one slice inside a larger universe with one more dimension. The anomalies would be caused by fields present in this bigger space outside our world. We see the details of this model on Professor Brand's blackboards in the movie. The universe would contain 3 brains: our brain, a brain above, and a brain below, forming a sort of sandwich. Between these 2 brains, the geometry of the universe would be curved into an anti-de Sitter geometry, a geometry allowing distances to be greatly stretched above and below our universe, such that gravity cannot escape. In fact, in our universe, gravity propagates in all directions, and its intensity is therefore distributed over spheres, which is why the force of gravity is inversely proportional to the square of the distance, just like the surface of a sphere. But if we were to add an extra dimension of space, gravity wouldn't form spheres, but hyperspheres extending beyond our slice of universe. And gravity would decrease like the cube of the distance, which we obviously do not observe. With the anti-de Sitter warping, gravity remains confined near our universe and still behaves as 1 over r squared. The other 2 brains help in delimiting this warping, leaving enough volume outside for possible adventures within the 4th dimension. This is a necessary precision to justify the end of the movie. Back on Earth, Murphy has now taken over from Professor Brand in their quest for gravity. It's now her task to find a solution to the equation and describe the nature of the fields to explain the anomalies observed on Earth. Although the professor's model seemed promising at first, no results follow, and Murphy ends up realizing what he had known all along without telling her. To complete the model, they need information about the quantum nature of gravity. Murphy must understand what happens at a point where gravity meets quantum, for example, by diving near the singularity of a black hole. Coincidentally, this is exactly what her father Joseph Cooper is doing in another galaxy. Following TARS, Cooper detaches himself from the Endurance and falls towards the horizon of the black hole. Can he survive without being spaghettified? Up until the 1960s, singularities were considered as point-like. In the 1970s, however, physicists understood that these singularities undergo chaotic distortions. They are known as BKL singularities. In the 1990s, researchers discovered that when we fall into a black hole, all the matter falling behind us seems to pile up because of the slowing down of time. We face a mass inflation singularity. Finally, we discovered around 2010 that older black holes have a 3rd singularity, stemming from the accumulation of matter that fell prior. This singularity is gentle. It generates relatively weak tidal forces. While this is still highly speculative, it might be possible to survive there, but we would have to dive almost at the speed of light to prevent the other singularity from catching up with us. This is precisely the advice that Romilly offers Cooper in the film. Gargantua is an old black hole containing a gentle singularity. He could survive it by diving at high speed. It is this possibility, although very speculative, that Nolan chose for his movie. In a mysterious way, Cooper manages to accelerate enough to hit this singularity first and survive. No one knows what lies at the center of a black hole. We would probably need a theory of quantum gravity. Nonetheless, in the movie, Nolan imagines that when Cooper hits the singularity, he is transported by a 4-dimensional object called the Tesseract, an object believed to have been placed there by the same beings who opened the wormhole. This Tesseract is a sort of 4-dimensional cube. While a 3-dimensional cube's faces are 2-dimensional squares, The Tesseract's faces are not squares but three-dimensional cubes, and this structure allows for Cooper to stay inside one of the faces of the Tesseract while the Tesseract transports him back to Earth, all the way to Murphy's room. By the way, if this journey feels quite fast despite the huge distance, it is because the Tesseract has been lifted above our brain into the anti-de Sitter warping we mentioned previously, where distances are greatly contracted. The Tesseract asked, which is possible because light can travel within the faces of the Tesseract up to his eyes. However, in the model imagined by Nolan, light cannot go back in time from Cooper to Murphy. He therefore has no way to communicate with her. At least this is until Cooper discovers that gravity can cross this barrier and return to the past. An idea which is probably inspired by the fact that in theories describing universes with additional dimensions in the context of brain cosmology, all fundamental interactions are generally confined within the brains except gravity, which propagates through all dimensions. Cooper can therefore send the quantum data to Murphy using gravity, giving his daughter all the elements necessary to solve the equation. We finally understand that he was behind the gravitational anomalies from the beginning. Recall once again, though, that the things we have just described are simply the physical rules set by Nolan for this very speculative sequence of the movie. Thanks to the data, Murphy understands that it is possible to control gravity. We can reduce the intensity of gravity on the surface of the Earth to lift off a huge space station and save humanity. The Cooper station, a large centrifuge, thus heads towards Saturn to cross the wormhole. For our last calculation, let's try to determine the dimensions of this space station. We could imagine several methods, but let me propose an unexpected approach. The ball experiences no force and therefore moves in a straight line at constant speed. But from the inside, the trajectory of the ball seems curved because we are spinning with the wheel. At this stage, we don't know the parameters of this trajectory: the speed of the ball, the angle of the trajectory, the radius of the wheel, and its rotation speed. But we see in the movie that the gravity in the station is similar to Earth's. This gives us a restriction on the rotation of the wheel. It must spin at a precise speed to generate this gravity. We also know that the ball ends up breaking a window above the field. We can therefore restrict the angle of the trajectory such that it reaches a point above the field. Watching the scene, we can time the trajectory of the ball and measure 4.6 seconds between the hit and the impact. And we can then estimate its initial speed by analyzing frame by frame and comparing to the size of the player. We find an estimate of 30 meters per second. With all these restrictions, we determine the radius of the wheel, approximately 50 meters or 100 meters in diameter for roughly 300 meters in circumference. A relatively small station which would rotate at 4 revolutions per minute. The trajectories of baseballs would be chaotic, to say the least. With other methods, by comparing with the size of a building for instance, we find very different values, sometimes even 1 kilometer. I'll leave it up to you to develop your own techniques to estimate these dimensions. Born from the creative mind of an expert in relativity, Interstellar is a unique movie with breathtaking visuals. Through these few calculations, we can appreciate the attention to detail brought to the construction of the scenario and delve deeper into issues that may not seem obvious at first viewing. As a conclusion, let's enjoy once again some of the simulations we've built throughout this video.